Lotfy channel, where advanced research becomes clear, engaging, and accessible. Today, we explore a remarkable study that pushes the boundaries of modern photonics. Scientists created 6 innovative cholesteric liquid crystal mixtures, each designed to control light itself. By carefully adjusting the ratios of 3 cholesterol-based molecules, they discovered how to tune photonic bandgaps across the infrared, visible, and ultraviolet spectrum simply by changing temperature. 2 mixtures AMJ3 and AMJ4 proved exceptionally powerful. They showed the widest tuning range and the strongest optical response thanks to the appearance of a rare and highly twisting phase called TGBA star. This phase allows the material to reorganize its helical structure and shift color with remarkable precision. Why does this matter? Because tunable photonic materials are the backbone of smart optical filters, dynamic sensors, next-generation displays, adaptive laser technology, and eco-friendly structural colors, all built from low-cost, organic, and easily processed materials. Stay with us as we break down how this research opens new scientific, technical, and economic horizons in the world of photonic materials.
And Salah Lotfy channel, where global scientific research becomes clear and accessible.
هنا نحول الأبحاث العلمية العالمية إلى معرفة مبسطة مترجمة لك بلغتك.
Ici, la science est expliquée et traduite pour tous.
Ciencia clara, accesible y disponible en varios idiomas.
Wissenschaft, verständlich und mehrsprachig für jeden.
قناة For Science Salah Lotfy Channel. العلم للجميع وبجميع اللغات. تابعنا لاكتشاف المزيد.
Welcome to For Science Salah Lotfy channel. If you're passionate about cutting-edge breakthroughs, you're in the right place. Today, I'm diving into a study that's changing the way we think about light control and optical materials. The research is titled Thermal Control of Tunable Photonic Optical Bandgaps in Different Cholesteric Liquid Crystals Mixtures. That's a mouthful, I know, but here's the big idea. Cholesteric liquid crystals are famous for their helical self-organizing structures. This team figured out how to tune what's called a photonic bandgap, basically the range of light a material can reflect or transmit just by changing the temperature. Imagine optical devices or displays that adapt on demand, sensors that switch sensitivity, or smart filters that respond to the environment. The possibilities here are huge. What's really exciting is how the researchers linked tiny changes in molecular structure to dramatic control over light. This is a deep dive into the world where physics, chemistry, and engineering meet. Now, the minds behind this breakthrough are 3 Egyptian scientists at the top of their game. First, Professor Dr. Ahmad Mohammed Labeeb. He's an assistant professor and the head of the Liquid Crystals Laboratory at the National Research Center in Egypt. His leadership in material design and phase analysis was crucial for this project. Next, Dr. Yasmin Adil Ward, a lecturer in interior design and decoration at Helwan University. Her expertise in material textures and optical visualization added a creative dimension to the team. And third, Professor Dr. Mohammed Fikri Metwali Badir from Cairo University. He's a specialist in ultrafast laser physics and advanced photonic measurements. Think high-precision, high-speed diagnostics. Their work was published in the Journal of Molecular Liquids, Volume 340, Article 117179 by Elsevier in 2021. The rigorous peer review, received June, revised July, accepted August, published online just days later, shows how significant these findings are. This journal is a top spot for advanced research in soft matter and optical systems, perfectly matching this study's impact. Coming up, I'll break down how these materials are engineered, how their textures shift with heat, and what makes their photonic bandgaps so tunable. Stay tuned to For Science Salah Lotfy channel, like, comment, and share your thoughts on this revolutionary research. Have you ever noticed the brilliant blue of a butterfly's wing or the rainbow shimmer of a soap bubble? There's no paint or dye, just structure. The secret is structural color, created by microscopic patterns that bend and reflect light. Nature's been using this trick for millions of years, and now scientists are catching on. Imagine building with Lego bricks so tiny you can't see them, arranged in patterns that interact with light. That's what scientists do. They arrange molecules in repeating patterns to filter and reflect specific colors. Unlike chemical pigments, these colors don't fade and can even change on command. It's a revolution in how we create and control color, using physics, not chemistry. Most colors around us come from dyes that can fade and harm the environment, but structural color is vibrant, long-lasting, and eco-friendly. The key? Liquid crystals, a state of matter that's not quite solid, not quite liquid. You've seen them in screens, but some liquid crystals can self-organize into patterns that create brilliant, dynamic colors. These materials can change color with a simple tweak, like temperature. Scientists are now harnessing this to make color-changing materials. It's not just a new kind of paint, it's a new way to think about color. By controlling structure at the microscopic level, we unlock endless possibilities. Imagine materials that never fade, displays that use almost no energy, and colors that shift with a touch. This is the science of the future, happening right now. Ready to see how it works? Let's dive into the world of color-changing liquid crystals. Consider the following. Meet cholesteric liquid crystals, molecules that line up in layers, each one twisted slightly from the last, like a spiral staircase. This helical structure is the secret to their color. The pitch, the distance for one full twist, determines which color of light is reflected. Short pitch? You see blue. Longer pitch? You see red. When white light hits, only the color matching the pitch bounces back. It's not mixing paint, it's pure physics. These crystals act as natural light filters, reflecting one color and letting the rest pass through. The best part? The molecules self-assemble into this spiral, no tiny robots needed. Scientists can make large sheets of this material, all perfectly structured. And here's the twist. That structure isn't fixed, it can be changed, opening the door to dynamic, tunable color. This self-assembling, color-shifting material is easy to make and full of potential. The secret is in the twist, and the possibilities are endless. Next, let's see how we can control these colors, on demand. The story gets even more colorful from here. Let's keep going. Here's where it gets exciting. The color these crystals reflect can change with temperature. Heat them up, and the spiral tightens, shifting the color from red to blue. Cool them down, and the spiral loosens, shifting from blue back to red, or even beyond what our eyes can see. It's like a built-in, color-changing thermometer. At high temperatures, the material can reflect ultraviolet light and look clear. At low temperatures, it can reflect infrared and appear colorless. This means you can tune the color across the entire visible spectrum, and even into invisible light, just by changing the temperature. Scientists can engineer these materials to respond to tiny temperature changes with dramatic color shifts. Imagine materials that signal heat or cold instantly, or filters that block or pass specific wavelengths with a simple adjustment. This dynamic control is a breakthrough for science and technology. No batteries, no electronics, just smart responsive materials. The power to control light is now in our hands. From sensors to smart windows, the applications are endless. It's a rainbow on demand, built right into the material. The science is elegant. The possibilities are huge. Let's see how scientists fine-tune these effects. The next step, mixing for a miracle. Scientists experimented with 6 mixtures, AMJ 1 through 6, each with a different amount of twisting agent. The goal, see how changing the recipe affects color shifting. They kept the base liquid crystal the same, but varied the chiral dopant. By heating and cooling each mixture, they tracked how the reflected color changed. Most mixtures shifted smoothly from red to blue as they heated up, but 2, AMJ 3 and AMJ 4, stood out. These had just the right balance, showing a huge range of color shifting. They could cover a massive portion of the light spectrum. The scientists had found their star performers. With the right recipe, the color possibilities exploded. Let's see what this means for the future. AMJ 3 and 4 had the perfect balance, super sensitive to temperature, with a massive color range. AMJ 4 could shift from near-infrared through all visible colors to ultraviolet, all in one material. Imagine thermometers that change color instantly, or smart windows that keep buildings cool or warm by tuning the light they reflect. Cameras could see in infrared or ultraviolet just by adjusting a filter's temperature. Displays could be low power, easy to read in sunlight, and only use energy when changing. The ingredients are affordable, the process is simple, and it's environmentally friendly. By mastering molecular structure, we unlock powerful new technologies. These tiny, twisting molecules are shaping a more colorful, efficient future. Science is making the impossible possible. The spectrum is wide and so are the opportunities. The future is bright and brilliantly colorful.
Ever wondered why butterfly wings or soap bubbles shimmer with color? It's not always pigment. Sometimes it's the structure itself. On a microscopic scale, materials can bend, reflect, or filter light, creating vibrant colors and amazing effects. This science isn't just beautiful, it's the foundation for futuristic tech like smart windows and color-changing sensors. The secret? Materials called photonic crystals, which can control light in ways that could revolutionize computing, energy, and sensing. The real magic is tunability, the ability to change a material's properties on command, like tuning a guitar string. By tweaking temperature, pressure, or electric fields, we can make these materials adapt and respond instantly. One standout example is cholesteric liquid crystals, nature's own light manipulators found in mood rings and thermometers. Their self-organizing, twisting structures give them unique color-shifting powers. By understanding and harnessing these crystals, we're unlocking new ways to build the technology of tomorrow. Let's dive into how these materials work their colorful magic. So, what's a photonic bandgap material? It's a substance with a structure that blocks certain colors of light, like a fence that only lets some balls through. By controlling which colors are blocked, we can create filters or mirrors that change on demand. Tunability means we can shift which colors are reflected. Imagine a window that tints itself as the sun moves. Enter cholesteric liquid crystals, a state of matter between solid and liquid, with molecules that flow but also line up in order. Their special trick? The molecules twist into a helical spiral staircase shape. The spacing of this spiral, the pitch, determines which color of light is reflected. And here's the best part. The pitch is sensitive to the environment, especially temperature. That means we can tune the color just by heating or cooling the material. This natural built-in tunability is what makes cholesteric liquid crystals so valuable for smart, responsive technologies. Scientists are learning to harness this twist for everything from sensors to advanced displays. It's nature's elegant solution, now in the hands of engineers. Let's see how this helical structure actually works. Picture tiny rod-shaped molecules stacked in layers, each layer's direction twisting slightly from the one below, like a spiral staircase. The distance for a full twist is called the helical pitch, and it decides which color of light gets reflected. If the pitch matches the wavelength of blue light, you see blue. If it's longer, you see red. Here's the cool part. Temperature changes the pitch. Heat makes the molecules jiggle and the helix unwind, shifting the color from blue to red. Cool it down and the helix tightens, shifting back to blue. This is how mood rings and thermometer strips work. Your body heat changes the color. Think of it like a slinky. Compress it for blue, stretch it for red. By choosing the right molecules, scientists can fine-tune how much the color shifts with temperature. This lets them design materials that are super sensitive or cover a whole rainbow. It's all about controlling that molecular twist. Now let's see how researchers mix up these crystals for maximum effect. Scientists act like molecular chefs, mixing custom recipes of cholesteric liquid crystals for tunable color effects. They use three main ingredients: a base liquid crystal for structure, a twister molecule to induce the helical twist, and a tuner that makes the pitch sensitive to temperature. By adjusting the amounts of each, they create mixtures that shift color predictably as temperatures change. Each mixture is made into a thin film between glass plates, letting the molecules align and form their helical structures. To test them, researchers shine white light on the samples and measure which colors are reflected at different temperatures. This careful mapping shows exactly how each recipe responds to heat. The goal: find mixtures that smoothly shift through the visible spectrum over a useful temperature range. It's a blend of chemistry, physics, and creativity. The result? Materials that can be precisely tuned for real-world applications. Let's see what these experiments revealed. The results? By tweaking their recipes, scientists achieved precise control over color shifts, blue to green to red, as temperature changed. The best mixtures had just the right balance of each component, creating vibrant, predictable color transitions. Too little twist, and the colors were faint. Too much, and the reflection shifted out of the visible range. The most successful blends transitioned smoothly across the spectrum with small temperature changes. This isn't just a lab trick. Think smart windows that block heat, food packaging that warns of spoilage, or adaptive camouflage. These tunable crystals could power next-gen sensors, displays, and even light-based computers. By mastering the chemistry and physics of liquid crystals, we can design materials with custom optical properties. The ability to control light so precisely opens doors to a bright, colorful technological future. Thanks to the humble Cholesteric liquid crystal, tomorrow's tech will be smarter, more responsive, and more beautiful. The future of light is here, and it's dazzling. All right, let's dive into the nuts and bolts of how these Cholesteric liquid crystal mixtures were actually made and studied. First up, the ingredients. The researchers picked 3 cholesterol-based chemicals: cholesterol oleyl carbonate, cholesterol benzoate, and cholesterol nonanoate. These aren't your everyday chemicals. They're loaded with 8 asymmetric carbon atoms each. That's what gives them their strong twist and makes them perfect for bending light in cool ways. To get these all mixed up, each compound was dissolved in super pure chloroform, about 0.1 grams per milliliter. Stir it up, let the chloroform evaporate, and boom! You've got your raw material ready to be blended into 6 different mixtures, each with their own recipe. These were coded AMJ1 through AMJ6. Now for the setup. They used tiny glass cells, just 2 by 2 centimeters, and coated them with a special polyvinyl alcohol, or PVA layer. The PVA spun on at 800 RPM, dried at 4000 RPM, and then gently rubbed with velvet. Why? That rubbing lines up the molecules, kind of like combing hair in one direction. 2 of these prepped glass slides are stuck together with epoxy, leaving a gap just 200 micrometers wide. Then the mixture is drawn in by capillary action at just the right temperature, just above where everything turns to liquid. That way, the liquid crystal fills evenly and stays lined up. Next, it's time to look inside those cells. Using a polarizing optical microscope, the team watched the textures change as the temperature shifted. They saw all sorts of patterns: fan shapes, marble-like swirls, even broken fans. Each one tells you something about how the molecules are behaving and why certain mixtures reflect certain colors of light. To really nail down the phase transitions, the study used differential scanning calorimetry, or DSC. This measures exactly when the mixtures shift from one phase to another, crystalline to TGBA, pneumatic or isotropic, by heating them up and tracking their heat flow. Think of it as getting the molecular weather report for each sample. And finally, for the main event, measuring how these mixtures handle light. They used a high-res spectrophotometer covering everything from ultraviolet to infrared, 200 to 1100 nanometers. The cells stayed on a temperature-controlled plate, and as the heat was dialed up or down, the spectrometer tracked the shifting reflection peaks and band gaps. Some mixtures, like AMJ3 and AMJ4, showed the most dramatic color shifts as they warmed up, meaning they're especially good for tunable optical devices. The changes seen under the microscope matched perfectly with the spectroscopic data, confirming just how tightly you can control light with these materials. So, by carefully preparing, aligning, and testing these cholesteric mixtures, the researchers showed off a toolkit for engineering light in ways that could transform photonic tech. Stick around. Next, we'll see how these materials might power the next wave of optical innovations. Ever seen a mood ring or a laptop screen? That's liquid crystals at work. Materials that flow like a liquid but have the order of a solid. This in-between state called a mesophase, gives them their unique ability to manipulate light and color. Scientists are especially interested in cholesteric liquid crystals whose molecules twist like tiny staircases. The distance between these twists determines what color they reflect. Control the distance, control the color. This is key for smart windows and flexible displays. By mixing and heating different chemicals, we can fine-tune these materials for new technologies. We created 6 mixtures, each with a slightly different recipe, to see how they affect color and light. Our goal? Find the perfect combination for maximum control over color and light transmission. This research is about precision, tweaking ingredients to unlock new material properties. By observing these changes, we're designing the materials of the future. Let's get started. Every recipe needs the right ingredients. Ours, 3 key chemicals. First, cholesterol oleocarbonate, COC, the foundation, forming stable, twisted structures. Next, cholesterol benzoate, CB, a mesogen that keeps molecules orderly and stabilizes the mixture at higher temperatures. Finally, cholesterol non-anoate, CN, the temperature-sensitive component that shifts color as it heats up. COC gives structure, CB adds stability, and CN brings dynamic color change. By mixing these in different ratios, we can custom design liquid crystals. We made 6 mixtures, AMJ1 through AMJ6, each with a unique balance of stability and color shifting ability. More CB means more stability. More CN means a broader color range. This balancing act is molecular engineering in action. Each mixture is a step toward tunable, high-performance materials. With just 3 building blocks, we unlock a world of optical possibilities. Science is awesome. Let's see what happens next. With our 6 mixtures ready, we used a polarizing microscope to reveal their hidden colors and textures. At room temperature, most showed intricate fan-like patterns, evidence of their twisted molecular structure. As we heated them, the colors shifted dramatically, red to green to blue, just like a mood ring. Each mixture behaved differently. Some, like AMJ3, transitioned smoothly through the entire visible spectrum over a small temperature range. Others had more limited color changes. We also saw rare phases, like the blue phase, appearing as colorful mosaics at certain temperatures. The recipe mattered. More CN led to broader, more dramatic color shifts. More CB meant subtler changes. This direct link between chemistry and color is exactly what we wanted. By adjusting ingredients, we can design materials for specific optical effects. Our experiments proved we can control color and texture with precision. It's science you can see and use. The next step, measure their thermal properties. Let's dive in. To understand our mixture's stability, we used differential scanning calorimetry, DSC. DSC measures how much heat a sample absorbs or releases as it changes phase. Each mixture produced a unique thermal fingerprint, showing exactly when it shifted from solid to liquid crystal and then to a simple liquid. These transition temperatures are crucial for real-world applications. 2 mixtures, AMJ3 and AMJ4, revealed an extra phase, the superstable TGBA phase, just before becoming a regular liquid. This phase acts as a bridge, making the material exceptionally stable and responsive. Mixtures with more CB had higher clearing points, meaning they could withstand more heat before losing their special properties. This data helps us rank mixtures for thermal ruggedness. For devices like smart windows, stability at high temperatures is essential. Our tests showed which recipes are best for robust, tunable materials. With this knowledge, we're ready to explore their optical superpowers. Let's see how they control light. Onward. How do these crystals control light? We used a UV-vis spectrophotometer to measure which colors each mixture reflected as they heated up. The key, the maximum reflection wavelength, which shifts from red to blue as temperature rises. This creates a photonic bandgap, a range of colors the material reflects, blocking others. The width of this bandgap determines how pure and broad the reflected color is. Chemical composition had a huge impact. AMJ3 and AMJ4 had the widest, most tunable bandgaps. As their color shifted from red to blue, the bandgap energy increased. Some mixtures reflected narrow, specific colors. Others, like AMJ3 and AMJ4, could tune across the whole visible spectrum. This tunability is the essence of photonic devices, precise, repeatable control of light with a bit of heat. Our results show how to design materials for custom light filtering. The right recipe means total control over color and wavelength. These are the building blocks for next-gen optical tech. Let's see what the future holds. The possibilities are endless. What does this mean for us? We're closer than ever to smart adaptive technologies. By mixing CoC, CB, and CN, we created materials with tunable, temperature-responsive colors. AMJ3 and AMJ4 stood out for their broad, stable color range, perfect for advanced devices. Imagine windows that tint automatically to block heat, or displays that shift color with a touch. These crystals could power sensors, thermometers, and low-energy, vibrant screens. Their sensitivity makes them ideal for detecting tiny temperature changes. Our work shows the power of molecular self-assembly, simple ingredients, complex results. The right recipe unlocks both wide color tuning and thermal stability. This is the first step toward a smarter, more colorful world. The future of technology is bright and it's built on liquid crystals. Consider the world changed.
As we reach the end of this episode, I would like to express my deepest appreciation to the brilliant researchers behind this remarkable work. Their dedication, precision, and creativity have brought us a deeper understanding of one of the most dynamic materials in modern photonics. My sincere thanks go to Professor Dr. Ahmad Mohammed Labeeb, Assistant Professor and Head of the Liquid Crystals Laboratory, Central Network Laboratories, Microwave Physics and Dielectrics Department, Physics Research Institute, National Research Center, Egypt. Dr. Yasmin Adil Ward, Lecturer, Department of Interior Design and Decoration, Faculty of Applied Arts, Helwan University, Egypt. Professor Dr. Mohammed Fikri Metwali Badir, Assistant Professor, the Ultrafast Picosecond Laser Laboratory, Department of Physics, Faculty of Science, Cairo University, Giza, Egypt. Thank you for this outstanding and truly fascinating contribution. Your work has offered tremendous value to our viewers and to the scientific community. And finally, to all our wonderful followers of For Science Salah Lotfy channel, thank you for your continued support and curiosity. I am Professor Dr. Salah Lotfy from the Egyptian Atomic Energy Authority, and I invite you to share your thoughts about this research in the comments section below. Tell us, what part of this study impressed you the most? Which applications do you think will benefit first from tunable photonic materials? Your engagement helps us grow and brings more science to more people. See you in the next episode. And as always, stay curious.